All right, so in 5.3, we're going to talk about what's called the fundamental theorem of calculus, and there's two parts of it. So let's talk about the first part real quick. It's we don't use it very often, so we won't have to spend much time on it. But it's part one of the fundamental theorem of calculus, and it says this: suppose we have a function defined this way. Call it capital F of x, is defined to be the integral from a to x of f of t dt. Okay, that's kind of an odd function, but that's it, right? So you plug in x, and x becomes this upper limit of the integral, and so then you try to find the net signed area from a to x of whatever function is right here. There's no real relationship between capital F and little f necessarily. All right. What's more important is we've got this structure right here. Well, the first part of the fundamental theorem of calculus says, well, if you want to take the derivative of this function, it's simply f evaluated at x. Okay, so let me put that in a little more concise terms. If you ever need to take the derivative of an integral, you just get this function back. Let me write it this way. If I take the derivative of an integral like that, the derivative and the integral cancel out, and we're just left with f evaluated at that upper limit. Okay, so what we're going to see is these integrals that we use are like inverses of the derivatives. Okay, so that's what you're going to see with that. Let's talk, though, and this is the real important part of the fundamental theorem of calculus. Let's look at part two. And it has to do with what we call definite integrals. And you'll remember that a definite integral is an integral that has limits. Okay, so we're looking at evaluating limits, and this is what we've been evaluating integrals. This is what we've been focusing on. Chapter 5 is evaluating these integrals, and we've been approaching it, either by using a Riemann sum or by hopefully graphing this and realizing that represents the graph we get gives us some friendly geometric shape. But in general, we just want to be able to evaluate integrals for any kind of function, not just the friendly ones that we've been talking about. So how do I evaluate an integral without doing Riemann sums and, in the more usual case where it's not a friendly geometric shape. So this is the key. This is the big thing. How do you evaluate integrals? Here's what part 2 of the fundamental theorem of calculus says. It says you find the antiderivative, and that's why we talked about antiderivatives. You find the antiderivative of this function. You evaluate it at b, and you evaluate it at a, and you subtract it. Now, sometimes we'll write it like this: f of x with this big bar a to b, and that means this right here. Okay, this is the big thing. If you want to evaluate integrals, you're going to use antiderivatives. So, as an example, let's evaluate the integral from minus 2 to 2 of x squared minus 4 dx. Okay, and again, we could do this using a Riemann sum and an infinite limit, but thanks to the fundamental theorem of calculus, we now know how to evaluate this integral, which will give us the net signed area, but we're just evaluating this integral. So all we need to do is we need to find the antiderivative of this thing, right? So we did antiderivatives at the end of chapter 4, and this is exactly why we did them, because we knew we were going to need them to evaluate integrals. So the antiderivative of x squared is x cubed over 3 minus 4x, right? And then I put this little notation here with my limits. And what that tells me is I now need to plug in the upper limit, the 2. So it's going to be a 2 cubed over 3 minus 4 times 2, right? Like that. So I plugged in a 2 minus, plug in a minus 2. Minus 2 cubed over 3 minus 4 times minus 2. Right? So I just need to work that out. 8 thirds minus 8. This will be a plus 8 thirds because it's a minus 8 thirds and then the minus distributes through. Minus 8, this turns into a negative, or sorry, back that up. It turns into a 16 thirds minus 16. Or, if I run my common denominator, 16 thirds minus 48 thirds, or a negative 32 thirds. So that should be the net signed area, or just the value of that integral. Okay, this is powerful. This is how we evaluate integrals going forward. We don't use Riemann sums. We don't cover the shape with rectangles. We just use this fundamental theorem of calculus. So let's try another one here. Let's evaluate the integral from 1 to 9 of x minus 1 over the square root of x dx. Okay, so we've got to find the antiderivative of this guy, right? Got to find the antiderivative. So to do that, we've got to use our little tricks for finding antiderivatives. In this case, we'll probably do it like this. Write it as x over square root of x minus 1 over square root of x, right? Break it up like that. Still haven't done any calculus. This is all just algebra. X over square root of x is x to the 1/2 minus 1 over square root of x is x to the minus 1/2 dx. Now we're ready to use, remember the only rule we really have outside of our definitions, the only rule we have for finding antiderivatives is the power rule. And so we have to make all of this change so that it fits the power rule. And so that's where we're at now. We want to apply the power rule. So it's going to be x to the 3/2 over 3/2 minus x to the 1/2 over 1/2 evaluated from 1 to 9. Now before I evaluate it, I want to clean it up a little bit. So it's 2/3 x to the 3/2 minus 2x to the 1/2, right? When I flip those denominators, evaluated from 1 to 9. If I plug in a 9, I get a 2/3, 9 to the 3/2 minus 2 times 9 to the 1/2. And then I'm going to subtract, plug a 1 in, 2/3, 1 to the 3/2 minus 2, 1 to the 1/2. Right? And so, got to remember your fractional, how fractional exponents work. Raising to the 9 to the 3/2 means you first take the square root and then you cube it. So it's going to be 2/3. The square root is 3, cubed is 27. Minus 2 times, of course, 9 to the 1/2 is just the square root. And then minus 2/3 plus 2, right? Because both of these are just 1. So it's 2/3 minus 2, or distribute the minus through 2/3 plus 2. Continuing this, we get 2/3 times 27, I think, is 18 minus 6 minus 2/3 plus 2. Right? So now it's just a matter of working this through. 18 minus 6 is 12, plus 2 is 14 minus 2/3. So, of course, it's 13 1/3. Or probably we'll just express that as 40 thirds is our area, or is the value of that integral, right? So, evaluating integrals, you're going to be using antiderivatives. That's kind of just really cool to me. If I want to find the area under some curve, and by the way, this little graph, if I draw this, right, this graph, this has a graph that looks like this, and there's 1, and there's 9, and so in evaluating this integral, I'm finding that area, which is an odd shape. It's not a semicircle, Okay, it's not a quarter circle, it's this weirdly shaped object, and I was able to find the area just using antiderivatives. I take the antiderivative of the function, and then I evaluate it at the two limits, finding the difference. That's a powerful result, and that's where we're going from here on out. When we evaluate antiderivative or integrals, we're going to be using antiderivatives.